So I like performance, and there's like many programming languages out there. So let's not talk about any programming languages. Let's talk about where computation actually happens. So I'm going to ignore anybody in the audience who's done anything with GPUs or FPGAs. You're just ignored right now. So it doesn't matter if you're Windows, Mac, or Linux. Doesn't matter if you're memory managed language or not. Computation happens somewhere. CPU is what most people are using. So in the same sense of when you're using a really smart third-party library and there's interesting algorithms and magic going on inside, you're programming against an interface and you don't care. But sometimes you want to look inside the library to understand it a bit better so that you can leverage it for being more efficient or whatever. Same's happening with your processor. Most of the time, you don't care. There's an interface. There is the assembly code and assembly that's going down to your processor. And the processor's doing little tricks and magic inside in order to make your programs better. So I'm going to give you a bit of an insight of what those tricks are to give you a bit of an intuition. So I'll do this through a few demos. So this first one here is adding in a random order. We're going to have an array of data. And all we're going to do is go to every single location exactly once, read it and add it to an accumulator, but in a random order. So read add, read add, read add, read add. You get the idea. So then I'm going to show like a chart that looks like this. And on the bottom axis is basically how small or large that array is. Is it a small array or a large one? On the other axis, we've actually got the bytes per second. So this is the rate that we're actually doing this operation. So at the top, we're looking at 20 gigabytes per second, and at the bottom, 450 megabytes per second. But what we're doing here is, what you expect to be a constant like operation and invariant on the data rate. You'd expect it to be a flat line. All we're doing is fetching and adding. But it's not just a flat line. So what's going on? This is a logical representation of the CPU when I did this benchmark a number of years ago. This benchmark has got nothing to do with multi-threaded. So even though there's 4 cores, let's eliminate 3 of those. And also, it's not multi-threaded. So the multi-core, the 2 processing units inside the core, doesn't matter. We'll treat it as 1 processing unit. Down at the L1, there is a data cache and an instruction cache. This has got everything to do with data and nothing to do with instructions. So I'll simplify that again. So what's happening when your processing unit is trying to fetch data to do some computation on? It's going to the nearest memory location available in order to actually do the fetch. And that is L1. L1 is the fastest round trip time you can expect. And if you can't find it there, it'll go off to like L2, L3, L4, and then out to main memory, which is talking to a different planet on this scale. So that's a gross simplification of what's going on. But that helps you understand what's going on in this graph. If our data, so this benchmark is just reading the data again and again and again to get some numbers. So the first iteration, it's having to pull it into the L1 cache. But then after that, our array exists completely within the L1 cache size. So that's where you actually get the flat line that we was expecting, because you're going to the L1 and back, and you get what you expected. But then when our data structure is even larger and it has to go to the L2 cache size or beyond, it doesn't fit completely in L1, and so this is why performance starts to drop off. So in this situation, where it's still less than the L2 cache size, it has to go to the L2, but it doesn't have to go off to the L3 and beyond. But some of the times when you're trying to find the data, it already exists within the L1, and it's not too bad. And then just for completeness, there's the L3 and the L4, and then off to main memory. The takeaway message that you'd have for this for your performance optimizations: try to minimize your memory usage. 2 reasons. The one that I showed you in this benchmark, you've got a small amount of data, you want it to be small and hot so you can use it again and again. And in the second situation where if you've got a large data structure that you're just going to use once, what you've ended up doing is pushing all the other data out of all the cache levels, which is actually going to cause the rest of your program to have to go fetch it. So another part of your subsystem, which needed to be hot, you've now made it slow. And I don't have time to go to the next bit, so this is going to be another talk at some other point. Thank you.